Hello class, today we are going to have a look on the moment distribution method for sway frame. Here, to determine the side sway and the internal moments at the joints using the moment distribution, we will use the principle of superposition. So this is the real case. Okay, when the frame, this is a typical frame, when the frame is subjected to a loading, okay, which is not symmetric, okay, and it will cause the frame to sway. The dotted line in red color is the deflected shape of the frame. If you notice that, there is a horizontal deflection for the frame. For the analysis, by using moment distribution method, we can use the principle of superposition, where at the stage 1, the analysis will be done considering no side sway, meaning that a horizontal restraint has been inserted to the frame. And because of these restraints, a reaction R, okay, will be exist, okay, and at this stage, the analysis will be for non-sway analysis. Follow the non-sway analysis procedure. Then the process followed with stage 2, which considering the side sway effect. So at this time, the artificial joint or the restraints has been removed. And there will be one loading, okay? R prime will be imposed at the restraints location with the same direction with the R. Okay, but right now in stage 2, this loading is termed as R prime. Okay, it is to note that no real load is located for stage 2. Okay, in stage 1, the real load is applied, okay, to the system. Okay, but in stage 2, the real load has been taken out, okay, and replaced with this artificial, this R prime loading, okay, at these artificial joints, okay, locations, okay. So this is a real structure again, okay, the procedure has been highlighted here, okay. We need to determine the real moments, okay, moments at the joint, okay. So there will be two analysis process or analysis stages, okay, involved here. The first one will be a non-sway analysis, okay, where right now because of the restraints here or with terms the artificial joint, okay, there will be force, okay, restraining force, term as R applied here, okay. So the real load is still maintained. So in this non-sway procedure, the analysis will be exactly the same as the non-sway frame or beam, okay, analysis. So in this stage, we aims to determine moment M1. Okay, so by moment distribution in the table, you will get n moments, okay, from the table, and we term it as M1. Okay, so this fixed M moment or initial moment has been taken due to the external loads or support settlement, okay, at the real case. Okay, so we need to determine the R. Okay, at the end, after the moment distribution table, we need to determine what is the value of the R. Okay, by using the equilibrium equations. Okay, so then we move to the another stage of analysis where we consider the sway analysis. Okay, in this sway analysis, the restraint has been removed and we will have loading applied to the system, which terms are prime. Okay, at the end of this analysis, we aim to determine moment M2. Okay, we will assume this R prime, the loading, will cause a deflection. So the fixed moment right now different from stage 1, it is due to the deflection. Okay, it is not deal with the applied loading here. Okay, it is solely due to deflection. And from the moment distribution table, we will get M2 prime. Then we need to determine the R prime value. Okay, so then we need to determine a correction factor, okay, which is R divided by R prime, okay, to determine the M2. Okay, I have to correct here. The moment distribution table will get M2 prime. Okay, in order to get the moment M2, we multiply with this correction factor, which is the ratio of R divided by R prime. So the final moments, okay, to obtain the final moment is M1 plus M2. And this M2 is R divided by R prime, M2 prime. Okay. So let's have a look on the sway or deflected shape of a sway frame. Okay. So now, let us have a typical frame in such. We will consider, there is a few instructions here, okay? Consider all the joints, okay? So now please look at the joint A, B, C, and D, okay? In the sway analysis or in the stage 2 analysis, we will have applied load of R prime, okay? And because of this R prime, the whole frame is going to sway. Okay, so now if you need to look at all the joints, we need to understand that joint A and joint D will not deflect since they are restrained by support. Okay, so we have fixed support at A and D. They shall not have any deflection, okay, or translation. Okay, so and joint B and C will deflect to B prime and C prime respectively as the load direction. So once the frame has been applied the R prime to the right, so B will move to B prime, C will move to C prime. Okay, it is to note that this must be perpendicular to the deflected members. Okay, so if you can see that we have, if we draw the B to B prime, C to C prime, and they will have this 90 degree, okay, to the this member AB or member CD. So now we just need to join all the joints at the deflected point. Okay, so meaning that now B, because of the R prime or C, has been moved to the new position, okay, which is B prime, but A and D still remain at all positions. So we just need to join all these joints. Okay, so means that the lines will be, the dotted line indicates the deflected shape, will be joined from A to B prime, okay, to C prime, and to D. Okay, so the dotted line would be the deflected shape for this frame. Okay. So now we need to determine the fixed end moments due to deflection. Okay. So I have to show you the equations, okay, to be used, okay, for this fixed end moment. Okay, so these will be the cases due with the deflection. I'm going to copy this and put to the page, okay, for our discussion. Make it a bit bigger. Okay, so the equations used for fixed condition due to the deflection, if you can see that, the deflections. Okay, so we will have, if you can see that the moment applied here is at the same direction, okay, clockwise. And we have a positive sign for 6EI delta over L squared for both the ends. Okay, so now note that joint B prime and C prime has deflected horizontally with the same amount of delta. Okay, it is to note that in this case, we must, there is one assumption that which is very important, that when the loading applied R prime, okay, so this B move to B prime and the distance C move to C prime must be the same. Okay, therefore we said that they have deflected in delta. We don't know the value. Okay, just put it delta. Okay, consider all members' maximum deflection value perpendicular to the member, and member A, B, and CD has deflected delta, while member BC remained the position delta equal to 0. Okay, so meaning that AB, if you look at, just place the AB exactly like a beam here. If you can see that if you place it AB here, you will find that delta is happening at B to B prime. Okay, similarly for CD, place it exactly like a beam, horizontal beam here, you will see that the deflection here is CC prime. Okay, but for BC, there is no deflection. Okay, because we said that the deflection must be calculated perpendicular, okay, to the element, to the member. Okay, meaning that you shall not determine the deflection value. Sorry. Like this. Okay, which this is not 90 degree. No, we need to get the maximum deflection, okay, which happening at the ends, okay, and it must be 90 degree, okay, to the member. Okay, that is why we use this value. Okay, we use this distance. This will be termed as delta. Okay, so then therefore by adopting the formula 6EI delta over L squared, say all the member length is L. Okay, let's say AB, BC, CD is L. Okay, because in the formula we need to put in the L. So therefore fixed moment AB equal to BA or equal to CD or equal to DC is equal to 6EI delta over L squared. Okay, but why it is negative? Okay, because I want to make it back to the original. So my moment will be in this direction. Okay, so remember in moment distribution method, counterclockwise is negative. Okay, so again, I repeat here. Okay, how to decide this fixed moment direction? Okay, you must have an idea saying that you want to push back, okay, the deflected shape to the original position. So let's say at C, C has been deflected to C prime. So to push it back or move it back, you need to push it to this direction. Okay, therefore, the fixed moment will be in counterclockwise. Okay, let us practice for a few more examples. And for fixed moment BC and CB, it must be equal to 0 because there is no delta involved for that member. So now let us have a look on the other case of the frame. Okay, so again, there is a horizontal force, okay, R prime, and it will cause this frame to sway. Okay, so let's have a look. So now, joint A and joint D will not deflect since they are restrained by support. So this A, D, they must remain, okay, at the same position, all position. okay, even though with the loading of R prime. But joint B and joint C, which do not have any supports, okay, will deflect to B prime and to C prime, okay, following the load direction. Remember, the tips is it must be perpendicular to the member, okay, for example, okay, so if you can see that B has moved to B prime and it must have 90 degree, okay, to this member AB. Okay, and then for member CD, if you can see that C is not moving to here, C prime, no, it is moving to here, C prime, with the angle 90 degree for this member CD. Okay, this is how you predict, okay, the deflected shape. Okay, then you link the new position of the joints. So remember A and D remain at the position. So what you can do now is to join A to B prime, to C prime, and back to D. So the red dotted line will be the deflected shape, okay, for this sway frame. Okay. So now we need to determine the fixed moments. Okay, let's say we have an angle given the 60 degree. Okay, remember our okay, before we applied the equations, we need to know where is the delta, deflected value. Okay, remember the deflection value, we must take the maximum, okay, which is happening at the ends, okay, of the member, and it must be perpendicular to the member. Okay, for example, member AB. So where is the deflection value? It will be this one. Okay, because this distance is perpendicular to member AB. Okay, and we give a naming of the deflection, a symbol, okay, to represent this. So let's say we use delta. Okay, so remember we have said earlier, okay, the B and the C must deflect horizontally with the same amount of deflection. So meaning that this B to B prime horizontal, C to C prime, I thought about, I'm telling about the horizontal deflection must be equal. So therefore, I can put it here, delta as well. Again, so B to B prime or C to C prime must have the same horizontal deflection. Okay, this is our assumption. Okay, you must apply that. So we can put it delta, okay, for both of these horizontal deflection. But this deflection, the one that I have pointed here now, is not the deflection for member CD. Because this, if I draw a line here, this is not 90 degree. The 90 degree is here. Okay, where the distance is talking about C to C prime. Okay, so probably you can guess now what is the deflection value for C to C prime. Okay, so if I circle here, I put it bigger. Okay, you can see that C to C prime here is delta double prime. Okay, and we already know that C to C prime, the horizontal deflection is termed as delta, similarly here. Okay, this value is just given. Okay, you can put any other value, B, C, okay, but here in my case, I will put delta is a horizontal, okay, deflection, and CC prime, I use delta double prime, and the vertical distance, okay, for C to C prime, I use delta prime. So you can see that for member CD, okay, so we are talking about this because this is 90 degree to member CD. Okay, therefore I use delta double prime. How about for member BC? Oops. Okay, member BC has deflected delta prime, the vertical one. Why I say so? Because if you put a line here, okay, it is remember your member BC is horizontal, right? Okay, this is the deflection. Okay, so it is 90 degree to the member. Okay, so yeah, this is the rules. The deflection taken must be maximum and must be 90 degree to the member of your interest. Okay. Okay, so once you already identified the deflection, where member AB have deflected delta, member BC deflected delta prime, member CD deflected delta double prime, please use this in use a triangle, okay, to show the relationship, okay, between this deflection. Okay, as what we have taken out just now. Okay, the horizontal is delta, vertical is delta prime, and diagonal is delta double prime. Okay, now we can know that fixed moment for member AB must be same with BA, and using 6 EI delta over L squared. Okay, so the delta here, we use delta because member AB deflected delta. Okay, so similarly, fixed moment BC equal to CB. Okay, we use delta prime in the equation because BC deflected delta prime. And for CD, we substitute delta double prime in the equation. But now the questions come. How about negative and positive and negative? So maybe let us move back to our previous this. Okay. So now let's look at AB only. Okay. Now B is the deflected point. We want to push it back or rotate it back to the original. So what you should do, you shall rotate in this direction. So you have a negative value of the fixed moment. Okay, so then for member BC, if you can see that the deflected point is C prime and you need to move it back to C. So what you need to do, you need to push it in such a way. Okay, so this is fixed moment for BC. Okay, so because this is the, don't confuse with CD because you are referring to member BC right now. Okay, you want to push it back such that C prime can turn back to the C. So this is a fixed moment and it is in clockwise manner, so this is positive. Okay, then for CD, if you look at that, this is C prime is the deflected point and CD is here. You want to move this C prime back to C. So you push this deflected shape here. Okay, so the fixed moment for CD will be negative as well. Okay, negative, positive, negative. Let's see. Okay, so here we have negative, positive, negative. Okay, but we couldn't have so many unknowns here. We only want one unknown. Okay, so you can substitute in your creativity form, but will remain only one of the unknowns. Okay, so in this case, we choose delta double prime, meaning that all the other equations will be written in delta double prime. To do that, we need to find the relationship between delta, delta prime, and delta double prime. Therefore, we choose the triangle here so that we can use the trigonometry principles, okay, to find the relationship. So now we can know that sin theta, 60 is given to you, okay? Sin theta is equal to delta divided by delta double prime, right? So you can find the relationship between delta and delta double prime. So you can say that delta is equal to delta double prime sin theta. Then we find another relationship between delta prime and delta double prime. So you can find out that cos 60 is actually delta prime divided by delta double prime. So you can form another relationship where delta prime is equal to delta double prime cos theta. So we can substitute this into the equation. For example, fixed moment AB, you substitute this equation delta equal to delta double prime sin theta into here. Okay, so you get the new equations with delta double prime inside there. Okay, similarly, delta prime, you can also substitute into these equations for fixed moment CB. Okay, then you can get a new set of these equations. So, but if you can see that now, all of this fixed moment is in one unknown. Okay, so this is the some treatment that you need to be having the skills so that when you are ready with this, you can the remaining of the procedure is actually quite similar. Okay, so now, oh, how about this? Can you determine this? Oops. So for today lesson, okay, please try this. Okay, determine the fixed end moments for this swirl frame. And since I do not draw the R prime direction, yeah, please have your R prime direction this way. Okay. So for today lesson, I would like to also share, a complete example. Okay, how to give you an idea how to solve a swirl frame by using a moment distribution method. Okay, if you can see that. Okay, this is our real case. Okay, so we are going to go start with the non-sway analysis for stage 1 to determine the M1, and we're putting a restraint, okay, so that the frame will not have a side sway. Okay, so but we still remain the loading. Okay, then we take out the loading and we apply the R prime, means that we are actually cancel, okay, this R and R prime in the principle of superposition, and it will actually equal to the real problems. Okay, so in stage 2, we need to determine this M2 and the R prime. Okay, first of all, you need to determine the DF. Okay, the distribution factor can be determined exactly like what you have experienced in beam and non-sway examples. Okay, for example, this is a frame with fixed at A and D. Okay, so we use 4 EI over L. Okay, for A and also D. Okay, and we use the remaining BC, CD, AB, we use 4 EI over L. BC, we use 4 EI over L. And also CD, we use 4 EI over L. Okay, because all of them are fixed condition. Okay, and we have DFA and DFD is 0 because it is a fixed condition. Okay, so you can determine your DF. And for non-sway analysis, we have 16 kilonewton acting on member BC. So you need to determine the fixed end moment due to the loading 60 kilonewton. So you can get the appropriate case, okay, to determine the fixed end moment BC. So if you can see that we use this PB squared A over L squared. The B here is talking about this B. So in this case, the B is 4 meter. Okay, 4 meter. And A is talking about 1 meter. Okay, so you have this one. And the total length is 5 meter. Okay, so and it is negative because at these ends, we have anti-clockwise, counterclockwise. Okay, so it is negative. Okay, so for this one, the A and B is talking about A and B here. And the P is 16 kilonewton. Substitute all this in, you get 2.56. So similarly, like your non-sway frame analysis, we put the F in, put in the fixed moment, carry out the balance and distribute, carry over, okay? So then ends up, okay, with this summation moment. Okay, here, okay, this summation moment we term is as M1. Okay, after you determine the M1, okay, so we need to determine R. How to determine the R? Okay, we need to determine, we use the equilibrium equations to solve for R. For example, R is in X direction. And if you look at the system, okay, sorry, I shall add, please add in my notes. Okay, so in this case, we have 16 kilonewton. Okay, but 60 kilonewton is not the horizontal force. Okay, we also have a AY. We also have a MA. Okay, if I would like to draw the whole DY and the MD, the whole, the complete, complete free body diagram. Okay, but the one that deal with the horizontal forces will be the R, AX, and also DX. Therefore, we need to determine the AX and DX first. Okay, so how to determine the AX and DX? We draw the free body diagram of member AB and for member DC. Okay, so for member AB, we are going to put in the end moments, okay, from the table. For example, 2.88 positive, which will be clockwise, and 5.78 positive will be clockwise as well. Okay, then taking summation MB equal to 0, okay, then you can get AX value. Okay, similarly, you apply for member CD. Okay, once the AX and DX has been obtained, okay, in the determined direction, then we apply summation Fx equal to 0. So in this case is AX is positive, AX minus DX minus R equal to 0. So you get the R is equal to a value 0.92 here. So now, after the stage 1 completed, we obtain M1 and obtain the R value. We need to proceed with the sway analysis. In this sway analysis, we need to put in the moment distribution table with the fixed moment taken from the deflection. Okay, so if you can see that fixed moment is due to deflection. So now in this case, the deflection has been given a name, delta prime. Okay, you can use delta, no problem. You can use delta double prime, no problem. Okay, so in this case, they have put in very clearly the deflection, horizontal deflection. B will move to B prime, C will move to C prime with the same value of delta prime. Okay, this is what we have assumed. Okay, make assumption in this sway analysis. Okay, then we can get the fixed moment is equal to negative 6 EI delta over L squared. Okay, so 6 EI, the delta here is delta prime, and the length is 5. Okay, and you will get all the fixed moment A, B, BA, C, D, and DC. There are only 2 members that have subjected to deflection. Be careful. Member BC do not have any deflection. Okay, so and we will have a negative because it will be acting counterclockwise to push this deflected shape into the original position. Okay, so if you can see that there will be all negative 6 EI delta prime over 5 squared. Okay, because these 2 members, they are having the same deflection delta prime and same length, 5 meter. So since all of this has the same value, okay, so we are going to, we cannot use the unknowns to put in the moment distribution table. Okay, we need the exact value. Okay, so therefore EI delta prime, we are going to assume with any value. Okay, so here the EI delta prime has been assumed some value. Okay, but instead of EI delta prime, in this case, they are actually assuming the whole thing 0.24 EI delta prime as negative 100 kilonewton meter. Okay, but if there is so many different ratio here, okay, I would advise you to put, let's say, take EI delta prime as 100 kilonewton meter, let's say. So in this case, if I take this, EI delta is 100 kilonewton meter, so I will get here 24, negative 24, negative 24, negative 24, negative 24. Okay, and I can put it in my this moment distribution table. Okay, so this is talking about a ratio right now. Okay, so any value you can put in. Okay, for example, if you don't want the 100, you want the 1000. So this would be negative 240 here. Okay, because the ratio are the same in this case, so they directly take the whole thing as and assume it one value. So in this case here, all the fixed end moment is negative 100 kilonewton meter. So they put in the table. We repeat again the process. The DF, how about the DF? The DF is same. Okay, we only need to determine DF once. Okay, so the DF for non-sway stage and also the sway stage are the same. So the fixed end moment will be different because in this case we do not have any, we don't have the 16 kilonewton, but we have R prime here. Okay, so now we have put in the fixed moment again. We calculate, produce these n moments. Okay, and these n moments, after you get the n moments, you need to determine R prime value. How to get the R prime value? It will also same like how you determine for your R. Okay, meaning that you are solving the equilibrium, okay, of these structures in order to get this R prime. Okay, once you get the R prime, okay, so we are going to apply the formula. M equal to M1 plus the correction factor or ratio will be R divided by R prime, multiply with M2 prime. Okay, so in this table, what we get here, this moment is M2 prime. Okay, so you can put it here, your M1 value from the moment distribution table number 1. Okay, and the M2 prime multiply correction value. Okay, means that this 0.0164 multiplied with this value n moments. Okay, so you get these sets of M2 moments. So M just sum these moments from stage 1 analysis and stage 2 analysis. Then this will be your final moments. Okay, so once you get the final moments, you want to determine the support reactions or getting bending equations. Okay, that will be the subsequent works. All right, another things to highlight here is the R. If you look at the R here, 56 kilonewton, and it is acting to the right. Okay, and the R must be oppositely. Okay, so if you look at the R, okay, acting at the left, okay, with a positive value. So you must make sure this happen. Okay, R and R prime must have opposite value. Okay, means that one's going to left and another going to right. Okay. All right, I think so. I would like to share with you. Okay, so for today's lesson, you need to try. Okay, to draw the deflected shape of this sway frame and determine the fixed moment for this sway frame. And please also download from UFuture the tutorial to determine the distribution factor and carryover factor. Okay, so in that tutorial, if you can see that, okay, I've prepared several examples, okay, for you to practice, okay, how to determine the DF, okay, and how to draw this carryover path, okay, yeah, and there are other cases, okay, this is from the past year question, June. How about this? How about this shape of the frame? Okay, and more members. Okay, and how about if the frame is having a stiff, this hinge, internal hinge? What you should do? Okay, so with this, I end my lecture for this lesson. Okay, have a nice day.